Okay, so we're happy to have the second talk on the theme of intriguing connections to data analysis by Yang-Hui from London, Oxford, and Nankai. It's a delight to see you again. And the topic is machine learning mathematical structures. Please.
Thank you very much, Hisham, and thank you very much for having me here. It's such a great treat, especially for us from England, because we literally haven't seen the sun for over 2 weeks. And it's very nice to be here. Thank you. I think I also apologize that I think most of you have heard various different fractions of this talk, but at least I promise that because I will patch up, there will be a manifold of patching, so that at least there will be something new to every of you. But I'm happy to have you sleep anyway. So just want to start with a general comment that since this is this conference is very nice in tying together string M theory with mathematics, and of course it's to this audience I'm really preaching to the choir by saying that algebraic and differential and geometry and topology in any combination of these words and representation theory is the right language for physics, and this has been known for many decades. And indeed, string theory, one of the greatest assets of string theory is that it is a brainchild of this geometrization program. But I want to emphasize that perhaps less appreciated, and that's really been the last 10, 20 years or so, is that we're in a new exciting era of dialogue, and the night dialogue is how this dialogue has a dialogue with data. Of course, people think of data science as something fairly recent, but the beginnings of string data really should go back to the days of Candelas and friends in the late 80s and early 90s, when they were running punch cards on the CERN supercomputer. It's quite ahead of its time. But that's within this community of strings. But mathematicians have now really seriously, over the last 10 years, created these various things that are available online, especially the SAGE program, which is this umbrella program which attempts to link the various software. So GAP is for groups algorithms and programming. It's nothing to do with the Jeans Company. It's terrible because if you type GAP and the first 20 hits is all the genes, then you got to dig deep for this. That's a very bad name. LMFDB is the database of L functions modular forms, and GRDB is a very interesting one. I'll mention all these databases in a bit. That's the graded rings database, sort of a vast extension of the Kurzgesagt database. So this is all the polytopes you can ever think about. There. Everything here is on the order about 10 to the 10th, the size of the data. 10 to the 8 to 10 to the 9. And Macaulay 2 is very nice, and it interfaces through SAGE to GRDB. Macaulay 2 is the computational algebraic geometry software, which I think this community really likes, because we like explicit computation of invariants. Of course, in this for this community, I think probably the biggest theoretical challenge to string theory is the lack of selection criterion. Or can we put a metric on the landscape? This is very much, if Dave Berman can tell us how to find the Fisher information metric on this space of possible string compactification, I think it would be a very wonderful thing. And of course, this goes really way back to way back in the beginning of this century, and these various numbers have popped up into the consciousness of the public. I think the basic reason why we have such a vast degeneracy problem in the string landscape is really due to this very simple fact that algebraic geometry leads to combinatorics, and combinatorics leads to exponential growth. So any of these estimates is fundamentally because of essentially because of this type of problem. So for example, if you take the most famous database of Clavier manifolds, this is a very good and very concrete problem to think about. So a theorem due to Borisov and Batyrev in the early gosh, early 2000s, or no, early 90s, sorry, early 90s state that if you take a reflexive integer rational polytope, so what is that? You just take a polytope, a convex body, whose vertices are all integers, or lattice points, and it has a single interior point, and such that all of the facets are at distance 1 to that single interior point. If you consider such convex body, and you construct a toric variety out of this thing, and you take the generic the generic hypersurface corresponding to the anticanonical divisor, that is guaranteed to be Calabi-Yau. It was a very simple theorem that leads to a very powerful result, because this gives vast generations of Calabi-Yau manifolds. So just to give examples of dimension 2, so in dimension 1 there's 1. That's just a point. In dimension 2, this is actually known to the Italian school of the late Victorian times, that there are exactly 16 of such beasts up to SL2Z. Everything that's up here would be up to SLNZ. This is very beautiful. I love this set. I mean, so this was known to people like Del Pezzo, Fano, Segre. And you can just check it. You know, these are the only convex bodies with lattice vertices, which have only a single interior point, and such that all of the bounding surface, all the bounding facets is distance 1 to the single point, up to SL2Z. And there are exactly 16 of them. So according to Borisov-Batirev, what you do then, you take a toric variety constructed out of these things, and that's a two-dimensional complex object. It's a surface. It's what's called a Fano surface, Gorenstein-Fano surface. And then you take the anticanonical hypersurface in that, the anticanonical divisor, that will always be guaranteed to be Calabi-Yau. So in this case, if you take that, it will be a Calabi-Yau one-fold. And those are elliptic curves. So these are 16 very beautiful and distinguished elliptic curves. Now, so this was known in the 1890s. The next one is already unknown. And this is quite impressive, right? You had to wait over 100 years for physicists to know what the next number is. So the analog of this problem would be integer convex polytopes in 3 dimensions with a single interior point, and all of the faces are distance 1 from that point. And there is no solution except by brute force. So that's one of Kreuzer-Skarke's achievement, is even to answer this question that was posed over 100 years ago. How many of these suckers are they up to SL2Z? So it's a precise number, 4,139. This is wonderful. So, and then of course, but these, if you take the hypersurface in the toric variety constructed of these things, will be 3-dimensional ambient space minus 1. There will be Calabi-Yau two-folds, or distinguished K3 surfaces. At the time, of course, physicists were interested in the next dimension up because they wanted to do Calabi-Yau three-fold compactifications. So now that gave the very impressive number of 500 million. That's where this 500 million came from, the 473. It was a very precise number. It's an integer. It's this number, which Kreuzer and Skarke did on a Pentium machine for 6 months, if you even know what a Pentium machine is. Which is very impressive. I mean, this is 500 million points. This is about 5 gigabytes. It fits on your, Apple Watch now. But back in days, this is a serious thing to store such information. The point is that there is no theory to even know what the next number is. You can punch this in. You can punch the sequence into OEIS, and the OEIS will tell you we have no idea what the next number is. And experts like Kasprzyk and Benjamin Neal and all these people created this GRDB database to incorporate a lot of this information. But these experts do not even know how to even approach with the next problem. It's not even known what is the upper bound for the number of vertices in the next dimension. So this is a very wonderful problem that you can pose to a high school student, or at least to a very advanced Russian high school student, and tell him or her to solve this problem. but this has been posed for decades, and it's an open problem. We have no generating series for this. We don't know idea, no generating function for this, and that's the problem. So the growth rate of this, of course, is exponential because you've translated a problem about Calabi-Yau geometry to the classification of combinatorial problem of such a type of lattice polytopes. So there have been some preliminary efforts in just try to do them by. So one thing I want to emphasize that the actual number known, even within this data set of Calabi-Yau manifolds, is much, much, much bigger than this. Because these are just the ambient polytopes. You need to desingularize them by triangulating. So this, for the largest one, the largest polytope, the number of triangulation is estimated to be something like 10 to the 10 to the 5. So the actual, and we have nowhere to even check how many equivalent ones there are. So the actual number of Calabi-Yau threefolds, even within this database, is many, 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 many orders higher than this. So for example, even if you triangulate up to H11 equal to 6, you already have 10 to the 6, even in the tiny bit. And 6 is, so if you consider like Hodge number 6, and these Hodge numbers go up to 490. So we're talking about many, many, many more quadrillion Calabi-Yau manifolds. It is still a conjecture of Yau that in every dimension, the number of Calabi-Yau manifolds, the topological type of Calabi-Yau manifolds is finite. It could be very big, but it is finite. The number of possible things you can write in terms of its topology is finite in every dimension. We know that to be true for Fano varieties. That's a theorem. That's why Calabi-Yaus are so interesting, because they're exactly at the boundary between Fano, positive curvature, Calabi-Yau is zero curvature, and then general type. And we know general type is unclassifiable. I think it's an undecidable problem. But the Calabi-Yau is just at this cutoff, the boundary of zero curvature, but Yau still believes that this finiteness result, for compact smooth, I'm saying, is still finite. And that's a very powerful theorem if this is true. So with this kind of data, right, you know what to do. This is so this all started in 2017 by complete coincidence of various different groups. And most important fact is that in 2017, Saudi Arabia has admitted Sophia to be the first AI citizen. She has a passport. Here's an attempted data in plotting. So if you think about, well, this is sort of indicative of certain progress in string theory. So these are the starting dates of the various annual conference series. And you can see sort of a paradigm shift in terms of where the new ideas in string theory are going. One of the latest ones is this string data series, which Dave and Challenger and my students just ran the 5th version of a month ago. And this series, this current series, is actually the youngest one. So maybe this series is truly indicative of where the future of string theory is going, is the ideas of M theory and mathematics. So let me just be more specific about what kind of ideas that originally got me interested in this. Of course, I'm very much an amateur. I still remain an amateur in this data science approach to things. But at the core of the problem, it really boils down to this, after thinking about this for a while. So let's consider a typical calculation in string theory, or indeed a typical calculation in algebraic geometry. I give you some manifold, and you tell me its topological invariance. That's a very typical computation. The typical manifold in algebraic geometry can be represented in a very convenient way. So for example, you should consider this matrix by, this one there are many other ways to do it. I mean, this matrix in here, I've given you a Cauchy manifold, which is just you read out the multi-degree of the complete intersection polynomials that are embedded in projective space. You could represent this data also in terms of, you consider such matrices, for example, as integer polytope data, the vertex data of the Kreuzerschkarka and whatever. And a typical computation in algebraic geometry is to take one of these suckers, and you follow what Bourbaki tells us to do, which is to chase sequences until you're blue in the face, and get the number 22 out of it. Right? So for example, we know what to do. This was a wonderful book that really introduced, I mean, Hubsch's book is wonderful in the sense that it was the first textbook in algebraic geometry for physicists. And I mean, and then you know, if you read Hubsch coupled with Hartshorne and Griffith, then I think you'll be okay for a bit. And it's exactly, we know what to do, and it just chases the sequence. And the wonderful thing is that all of this information is now in Macaulay 2 and Sage. So in principle, I could type in any manifold or any algebraic variety and just hit return H11, H21, whatever, Betty 1, Betty 2. And for simple cases, it does extremely well. So certainly for dimension 1 and dimension 2, it does, you know, it's very good. You know, Sage does this extremely well. But the problem is, this is a very, very expensive way to do it. And there's a precise reason why this is expensive. It's because any computation in algebraic geometry must first pass through the Grobner basis. So if I give you a system of linear equations, right, the first thing you would do is to do Gaussian elimination, and then put it in the standard basis, then you're done. So that's a linear system. Algebraic geometry, or at least computational algebraic geometry, is nonlinear algebra. So instead of giving you a system of linear equations in multivariable, you're given a system of high degree variables in multivariable. And every computation in algebraic geometry, and subsequently anything you're ever interested in string theory, will boil down to one of these problems. Now, the analog to the Gaussian elimination procedure is the Grobner basis algorithm. It's a standard monomial basis for polynomials instead of linear ones. But the bad bit is Gaussian elimination is polynomial time, or polynomial complexity. Grobner basis is double exponential complexity. And that's what kills any Sage computation if you do anything serious. So in principle, I can take the Kreuzerschkarka database, and we can do it. I mean, it even reads it into Sage, and just say, hit return, compute, you do anything, right? Find cycles that you can wrap brains with, find orientifold planes. So they're all precisely algorithmic statements. But the problem is that the moment that you start doing, you have to go through the Grobner basis, and then you're sunk. Anything more complicated than the quintic, it'll struggle, because you'll get the number of terms in monomials grow so fast, you will be uncontrollable. Unlike linear elimination problems, which is Gaussian elimination. So, but what got me thinking about this whole thing is that, well, this problem of computing through some black box of you should associate the number 22 to this is not that different from associating the number 22 to this image. This image is just some image representation of this matrix. And I do mean that. I have said this in front of algebraic geometry. In fact, I was just at the algebraic geometry conference last week, or just 2 days ago, drinking heavily with Russians. That was great. This is my detox. This is my detox and sunshine. Thank you, Hisham and Urs, for detoxing me with sunshine and water. And I said this to algebraic geometrists, and they haven't killed me. So they do agree that algebraic geometry is an image processing problem. The entire field is just an appropriate image processing problem. That's fine. How do you process it? Whether you can find a clever way to process this field, that's trickier. But fine. To extract 22 out of this is series sequence chasing. To extract 22 out of this is really cheap, right? Because you can just do some simple cases with some neural network, Just like how you recognize these digits, and then you train, and then you try to validate. And of course, there's a big problem, like what David pointed out just before. You have a serious problem with interpretability. Just because you're getting, and also the fact that you don't always get 100% accuracy. Just because you get 99.9% accuracy, having done some sample training, and you get the right answer for this recognition problem, doesn't mean that one, you can actually get something meaningful out of it analytically, and I will address that in a minute. And two, how do you address the ones that you're not matching perfectly? But at some level, we are protected by this kind of theorems in neural networks. I won't bore you with the details of all these statements, but these are just very, very fancy ways of saying that neural networks are very good approximators, or machine learning algorithms are good approximators. And we know they are because at the end of the day, if you really think about it, I'll give you an algebraic variety and you want to compute, say, its Betty number. There is a formula. And the formula is going to be very, very complicated. But what we are doing, or what one could do with any such, for example, neural network, is to approximate that formula. Right? So to give you an example, if I give you a single projective space, Pn, and I want to compute the Betty number of Pn, I can just write that down. I know what it is. It's, I can't remember, some combinatorial. Hk of Pn is some combinatorial formula in n and k. Now you take Pn1 cross Pn2, now just 2. You're still okay. You have some kind of Kuhneth type formulae, and that goes, like Borel, Bott-Borel-Wahl kind of formulae. Now it gets a little more complicated, right? So it says, H0 of P1, say P5 cross P7 is blah. H2 is some n plus, 2 choose. So that gets a little more complicated. Now let's consider polarized projective varieties. Even if you consider single hypersurface in, say, P7 cross P8, okay, of degree 7,9. Okay, just very simple data. Your matrix is just 7, 9, 5, 4. You can do it. And now that has been done for cases. But even just considering that, writing down that formula, which is analytic, is horrendous. It goes on I should have given you an example. It's like, if your O of n, if n is bigger than 5 plus 7 choose 2, then it is equal to 1. But there's the regions are much, much more complicated, even for a single hypersurface in the products of 2 projective spaces. So in that sense, what these kind of universal approximation theorems are doing is to approximate that kind of almost useless formulae. Because if you want to compute the Betty number of a projective variety, you won't want to do something like this. You would actually go to Sage and let Sage do that computation, because the analytic formula is useless. Right? In fact, many analytic formulae are useless, and they're much better to be done as an algorithm rather than as an analytic. Just, we have an analytic bias as mathematical physicists, but it is what it is. Mathematicians are fine. Mathematicians will tell you, pure mathematicians will say, well, there exists a formula. And, that's it. And it's exactly a perfect example where Borisov and Batyrev had that beautiful theorem, but Kreutz and Schkaker actually had to get the hammer and actually do the actual thing. So perhaps in that sort of idea, having a machine-learned, non-explicit formula is as good as what mathematics can ever give us anyway. So that's my first extreme viewpoint. And that is true for many of these cases, especially in algebraic geometry. So that, I think you've seen a lot of you have seen various versions of that, my sales pitch. But I've been thinking about how to actually extend that further from just string theory and algebraic geometry. String theory likes algebraic geometry because it gives us compactification scenario. But what about every single branch of mathematics? How do neural networks or how do support vector machines respond to other branches of mathematics? So let's start playing a game. I think you can probably all tell me what this sequence is. Sorry? Yeah. Sorry. Somebody yelled out an answer. Yes. How about this one? So, what is it? This is just to keep you awake, it's late afternoon. So we play a game. So this is a bit harder. So this is prime character for the odd integers. So if it's one, if it's this odd integer is a prime, and 0 if it's not. That's a sequence. What about this one? If you can just spot them, okay, this one you may almost do it, but if you can spot this one, you get a lot of money from Peter Sanak. So this one is the Liouville lambda function. So this one is if you take an integer sequence, you take the number of prime factors, then you just record the multiplicity. It's 1 if it's even, it's 0 if it's odd. The original Liouville lambda is +1 if it's odd, and -1, but I've shifted to be 1, 0. So here's the question. You didn't struggle with this. This you would have thought of a little bit. You may have come up with the answer. And this one, you really have to struggle a little bit. Is it true that a neural network would struggle in the same way? So how do we do this? You can very easily vectorize this representation and turn this into a supervised learning problem. Of course, you can do many other things. I know David likes unsupervised learning because that's totally automated. But so I like supervised learning because I like to supervise the computer to do. It's like maybe it's because I have two very small kids. So one way to vectorize this information is like if you take this long sequence, this is obviously an infinite sequence, you take a sliding window of, say, size 100. So now it's a vector. It's a vector in Z, well, in Z2, 100, and then you try to predict the next number. So you're going to have things that look like this. And then you can do your favorite algorithm. You can do something that's perfectly adapted to this one. So this is a binary classifier on a binary vector space. And a very good way to do is what's called a support vector machine, where you try to find the optimal separating hyperplane between ones and zeros. But do whatever. Do base classifiers, probably David's favorite. And then neural network, your kitchen sink. Try everything you can. And you'll find very quickly that with this kind of, if you vectorize this one in this representation, this one or this one, very quickly the mod 3 problem is solved with 100% accuracy. Because, even if, it's so simple that I guess a linear layer in a neural network will very quickly decide that this is some linear transformation problem. So that's good. That goes with our intuition that is indeed the simplest problem. So what I'm recording here, the first number is the naive precision when you test against the validation data. And the second one is chi-squared. So you want both of them to be as close to 1 as possible. In this case, it's just 100%. There's no way any simple classifier would not be able to distinguish this one. The prime one is a bit trickier at 80%. It's not, I've tried various other things. I'm trying to understand what exactly it's actually doing. So I tried to do things like training on mod 4 and mod 3, mod 5, mod 7, and then validating on the prime thing. And it also works around about this level. So it's kind of learning some kind of mod. It's doing some kind of linear transformation but learning that mod is exactly what the CIF algorithm is. right? So the Aristophanes sieve is how you would, the most inefficient way to detect primes is to do the brute force sieve method. So that is arguably still doable. I don't know why it's not doing any better. I couldn't find anything better than this, nor could I find anything that does worse than this. Yes? Oh, sorry, I just wanted, one is the naive precision one upon validation. So like, what did I, with a 2080 cross validation. And the second one is your F1 score or chi-squared. I just want them both to be close to 1. It's really, I want in this case, I want the 2x2 confusion matrix to be as diagonal as possible. Yes, so this one is, so the Liouville one says it's 0.5, meaning that it's random. It is really random. If I did a random sequence and if I generate a noise and make a classifier do that, it will return exactly this kind of, so the 0.5 means that I'm guessing 1 50% of the time, 0 50%, meaning that it's not doing anything. The 0.00, that's just the, it just says that my confusion matrix has chi-square 0. So it's completely randomly distributed. No correlation at all. I'm saying that I haven't been able to break this, but if you could find any neural network that does even a tiny bit better than this, I think Peter Sarnak will give you a lot of money. Because this is truly, the Liouville lambda, I was told by experts, is one of the hardest things in number theory. There are all this, Erdős, one of this, I'll tell you stories about how Erdős conjectured about the behavior of this, and Erdős actually got it wrong, and then there's this whole story. But it's not an easy thing to do. Yeah. Yeah, that's an extremely good question. So I tried various things. I even balanced the data by selecting more ones according to x over log x, because I know how it's did. Yeah, I did that and I still got this. And I tried that without, I still couldn't get any. I even building in the distribution, I still couldn't do better. But I'm not, it would be great if somebody could do just even a tiny bit of improvement on this would be very much appreciated by the analytic number theory community. But it is very nice that, just 3 problems that come to your mind in terms of increasing complexity. Now that complexity doesn't have really a formal definition, as far as I know. It's not computational complexity. It's not Kolmogorov complexity. It's just sort of complexity in terms of mathematical complexity. Perhaps this is a good measure of how complex a mathematical problem is. It's just that here's a math problem. It generates this data. Throw into 500 different neural classifiers and record that number, and that number is more or less, or average over them, that number is more. So this is what I'm trying to propose, a new measure of complexity of how hard a problem is. In terms of how bad would it be for you to recognize a pattern in this branch of mathematics? I don't have a formal anything better than that formal definition, but it would be very interesting to formalize that definition. Yes? Yeah, 20 is good enough. Yeah. Yes. Yeah. That's true. Well, that's another. That I also don't know. I mean, obviously 100 I chose at random, but I also varied it. So I tried 1,000, but then it becomes very expensive to do. But I tried 1,000, it didn't show any significant improvement. But then again, with primes, you never know what happens. So I tried windows of 1,000, anything from 100 to 1,000, I didn't see much improvement. But maybe it would be nice to see a plot of what, yeah, that's a, yeah. I can, we'll do that over dinner. That's plots. That's the wonderful thing about this. I mean, this kind of thing is unthinkable even 10 years ago, right? That's the point. The fact that I can do a learning and training problem like this over dinner on a laptop like this in a matter of minutes or seconds would be unthinkable even 10 years ago. And that's the true reason why everybody's doing it. It's because you don't need to go to some cluster to do this. I can just write a couple of lines in Mathematica and just do this training while we eat. I think that's sort of the paradigm shift. It's this free availability of the power of doing this. I think Christian was telling me that Christian was interested in this in the 90s, but back then we just didn't have the hardware to do this sort of experiments, and now we have the hardware to very cheaply experiment with this, right away, and that's kind of nice. So there we go. So I gave you 3 random problems. So let's just give all kinds of random problems. So that's what I did. I've been going kind of random over the last 5 years on just doing random stuff. So I think if you start to do like word recognition of my papers on arXiv now, I think I'm borderline crackpot, just because there are these random things that you do. But nevertheless, I'm very grateful to my fantastic students and collaborators over the last years on various different types of problems. I think Dave is certainly one of my physics friends that we've been trying to map out. There's data, just try to do it. And especially my fantastic team of students, some official, some unofficial. And I especially like to mention Ellie, because Ed and JK are done. They've got postdocs, and Ellie is the next. This is my little daughter, and hire her, she's great. So now let's do like pure philosophical speculation. Like, how does one actually do mathematics? Right? Well, you can go to the Russell Whitehead program of Principia Mathematica. You really should go back to Leibniz to axiomatize it line by line. And of course, this program was killed by Gödel, Church, and Turing because of incompleteness theorems. But I love this quote, and this is a quote from my friend Min-Young Kim, who is a very deep thinker. He's a number theorist, and also actually he's the director at Maxwell Center. He's a dear friend and wonderfully insightful person. He says, the practicing mathematician doesn't really care about Gödel. Seriously? Yeah. So that's a good quote. So, and I think it's this statement that really started the ATP program in some sense. So the ATP program is what people did despite these undecidability theorems of Church and Gödel and Turing. So you can see the dates. Even in 1956, incidentally, interestingly, that was the first neural network, 1956 or 57, around about that time, when they created the first neural network on a very large wall of photoreceptors in the basement of Penn or MIT, Penn-MIT collaboration, and they shone light on it to try to stimulate the neurons. So these guys devised some machine, some Turing machine, and they were actually able to prove some subsets of theorems from Principia. So that was sort of the beginnings of the ATP program, this program of, fine, don't worry about Gödel, can we write down every sentence of mathematics line by line and then construct its proof line by line in some appropriate language. So the state of art are Coq and Lean. I don't know much about Coq. Christian knows much more about Coq. Lean is great because Kevin Buzzard creates a lot of buzz about Lean. And Lean is great, and you can play with it. So what Kevin Buzzard's done is to take the entirety of the undergraduate curriculum at Imperial and put them into this syntactic form of Lean, every single line and every single line of his proof. And I think he's done it. No, he hasn't done it, but this is exactly what a problem that is perfectly suited for large parallel clusters of undergraduate students. So he's got hundreds of undergraduate students and graduate students recruited. Every theorem you learn, go and type it into Lean. So now they've got this huge database. And so he ran it, and it's great. So undergraduate mathematics is so far consistent. So in other words, Cauchy residue theorem still holds. The reason it's not entirely joke. It's entire joke. So in his ICM address just recently, he points out in these two really nice talks, he showed two abstracts. I really should point out those two abstracts. These two abstracts in Annals of Mathematics, I think in differential geometry, they state opposite things. So at least one of them is wrong. And Annals of Mathematics, is the most refereed journal of all science. I mean, everything is checked, and it still went past the referees. And they're either both wrong, or at least one of them is wrong. And it's gotten to that point that we cannot have human referees checking mathematics anymore. And this is just an example. It's going to get worse and worse and worse, just because it takes a couple of thousand lines of logic to even state a theorem. So that's what really inspired Buzzard to let's at least check that undergraduate level mathematics is consistent. Thank God it is, so it's okay, we don't have to go cry. And now there are other parts of it in graduate level mathematics. So Peter Schulze recently had one of his theorems verified by Lean, which is good. So Schulze, this is a pretty smart guy, I think. So Peter Schulze had a recent theorem, and he wanted to verify all the intermediate steps. He goes to Buzzard. Buzzard says, I have 500 graduate students who is going, no, not in that case. I have 50 graduate students who will type out everything to do with arithmetic geometry that could lead to an understanding of your theorem. And they checked it, and Peter Schulze was correct, of course. But what's interesting is that in the process of typing in this intermediate steps of this new paper of Peter Schulze's, this was just a few months ago, they found a better proof. It was kind of nice. Even Peter says, was acknowledging the fact that, oh, great, there's a better pathway towards this proof. Unfortunately, that pathway was not automated. It wasn't generated completely by Lean. You need human intuition to guide it, but who knows? And so that's one way. This is how you do mathematics part one. And that's exactly what I'm not going to talk about, because that's how I'm going to call this bottom-up mathematics. So this is a physics term. I'm borrowing this from physics, because you are building mathematics from bottom up. Every single symbol, every logical connector up. What the examples that I showed earlier is in the other direction. Right? We're generating mathematical data, and then we will pattern spot such mathematical data, and we will try to come up with conjectures, or at least try to guide us where to go with such direction. But this is very much how mathematics is done historically. Mathematics was never done ground up. We do ground up only as a retrospect. For example, we had countless examples, right? Newton and Euler were doing series long before the idea of convergence even was around, and so on and so on and so forth. There's so many examples. There's some kind of about fudging and intuition, and that's the great thing about neural networks, because they fudge, and that uncertainty is what gives us that sort of edge towards intuition. So I think I've said this joke so many times that, well, at least for the ones who haven't heard this joke, is that what is the best neural network of the 19th century? Well, it's clearly the brain of Gauss. So the brain of Gauss can look at this diagram and just say, well, this is clearly x over log x. And Gauss, I have no idea why Gauss even we would have guessed this, because this is 50 years before these guys even had complex analysis in order to prove it. So this is something that is exactly like what I'm trying to propose here, is that we don't have Gauss anymore, but we have billions of computers and neural networks which you can tap into data of such a type. Of course, there is no simple problems left in mathematics. That's all been done. If anything is simple, it would have been done by the brains of like the likes of the brain of Gauss. But we have much more sophisticated data that polytope, even a good one is the Kreuzerschkarka database. That polytope data even Gauss couldn't possibly read 473 million polytopes and make conjectures about their statements about such a type. But for a machine learning algorithm, that is really very useful. And even the BST conjecture, right? The BST conjecture started because Birch and Swinton Dyer were just mucking around. They plotted the order vanishing of an L function to the rank of elliptic curve. They plotted all kinds of things, and they noticed that these two are equal. Oh, great! I mean, that's a wonderful way of conjecture formulation, right? You throw in everything you know about elliptic curves until you notice that certain things are either equal or linearly correlated, and then you can make a conjecture. And of course, that was done on a basement computer in Cambridge in the 1960s. So you can see that I would say that was the first. We were talking about this over lunch about paradigm shifts and what constitutes a paradigm shift in science. In the 60s really was the first. That was the golden era when people were thinking about automation and computation. And then that program kind of died down a bit because the hardware wasn't there until now. And that's why, like right now, it's so important. This is why all these breakthroughs is because we finally got hardware to address what these guys were dreaming about in the 60s. Can you imagine if what Birch and Swinton and I would come up with today if they had our kind of computational tools? So I'm just going to give you some examples. How am I doing on time? I only have 10 minutes. Oh, good. Okay, so good. So I'm going to skip most of this because this is just, okay, I think I obviously played around with all kinds of data. Some highlights will be, I'll just give you some sample problems of highlights of this before I talk about something that's truly fun. So for example, if you plot the Cayley table of finite groups, and that's n by n, and then you pad it with 0 and plot in this r to the n squared space. And you're trying to separate out simple versus non-simple groups. A support vector machine can actually separate these two to this level of accuracy, which is kind of surprising because there are no theorems of such a type. In some sense, simple groups are truly different from non-simple groups. And if you really want to compute this, it's not an easy computation. So this is a proto-conjecture with Mignon. I don't know, we have no idea why. So this is the kind of games you play. I won't bore you with this. We're in 10 minutes. I will leave it. I will lead. So here you can do with finite groups. I'm glad Yao is interested in this, and I have to advertise because Yao says. So Yao has this new institute which was launched last year to do physics, mathematics, and AI. And Yao being Yao, he says, I need 10 billion, and the government says, when do you need it? I need it next month. And then it's done. Then a check was done. So this is a very civilized way of doing grant application. Yao makes a phone call, there's some dinner involved, and then there was 10 billion transferred within a month. This is the kind of how science should be done, I think. I won't bore you with, I'm just saying the various things. So here, let me go back to this number theory problem, right? So that's the Liouville lambda and the prime characteristic. Interestingly, if you translate your problems from hard, traditional, classical analytic number theory to arithmetic geometry, the accuracies certainly get much, much better. That's kind of intuition, because one doesn't solve Diophantine problems because they're hard. One solves Diophantine problems by translating them to problems on elliptic curves. That's the only shot we have of solving Diophantine problems. And indeed, that goes with our intuition that if your Diophantine problem is translatable to properties of elliptic curves, then your machine learning recognition type of problem suddenly gets much, much, much easier. So that's kind of nice. So far, I mean, of course, then you could probably find millions of counterexamples to what I'm saying, but I'm just trying to give you a very vague gist of what mathematics is in terms of hardness. And that hardness is something like this. If there's a numerical algorithm that does anything, I will bet you money that a machine learning algorithm will do better. It's inconceivable that there's a if there's a numerical algorithm, you've got a problem in the, over R. If you're working over R, then I cannot imagine. It gave me confidence because of this kind of problem. So here's an example that I was doing with Ashmore and Bird long before we really knew what we were doing. So here's an example. So if you don't find Ritchie flat Calabi-Yau matrix. It's just analytically, it's just too hard. So Donaldson gave this wonderful algorithm, which is sort of a balanced convergence algorithm to sort of, it's a fudge of the Fubini study, and then he proved that it converges to a Ritchie flat Kähler metric. And so it's a sophisticated algorithm, which is very expensive because you need to create more and more monomial bases in your Calabi-Yau. So we just naively took some linear transformation layer with some hyperbolic tangents, just a very simple feed-forward network. We sampled through some low-lying monomials, and with a little bit of high-laying ones, and then you could get precision as good as the Donaldson, but at almost 100 times faster than Donaldson. We have no idea what the network is doing, but it's doable. Even something that sophisticated in terms of creating numerical Calabi-Yau metrics. And then Douglas and Lara Anderson and friends, they really improved on this by not using Donaldson at all. Just pass through your points, and you're trying to associate a learning on the actual metric on that point. And they were able to get something very, very, very accurate very quickly. So numerical kind of stuff is really no problem. And then this big red arrow is going towards complex. I can't use the word complexity because I would just say hardness, because this is how I think logicians would agree with me. There is more or less some definition in mathematics of what hardness means, and it's going towards this direction. And this direction is more or less correlated with performance of your typical neural network. And that's a kind of a fun fact. Of course, there's a much more serious thing. Is how do you really raise precise conjectures? Right? So I mentioned this one about separating hyperplanes between simple and non-simple groups. And then there'll be various nice works over the years. I think Andre Lucas gave an exact formula for cohomology of surfaces by just studying enough points in your space of possible line bundles. And this really culminated in this paper that came out last year with this Nature paper of DeepMind, where they do exactly the sort of thing. They looked at 3.5 million knots. They plotted every possible dependency that could go in, and then did saliency, feature extraction, and then just did the regression on the key features, and they proved that theorem. Not unlike what Dave and my student Ed, a great student, I'm transferring him to you now, Dave. He's fantastic. And we wrote this paper on computing Hodge numbers for Calabi-Yau hypersurfaces, where we did feature extraction to see which one was the most possible, dependent on computing Hodge numbers. So, but this idea of getting into this direction of conjecture formulation is going to be, I think, a very major direction in mathematics. So let me just wrap up. Oh yeah, by the way, submit to this. It's great. This is launched this month, and I think this is trying to be a thing that tries to do mathematical data. Here's just last bit. Here's the fun bit. But can we do meta mathematics? So meta mathematics is fun. Of course, we had this conversation over lunch already. So in this paper, we basically stripped all the titles of the various sections of the archive to Ginsbach's horror. I think we're on his blacklist. If you look at the word cloud, you can't really tell the difference between HepTH, HepPH, and MathPH. So the most common words are model, quantum, dark matter, equation. Can you syntactically tell the difference between these sections? So this is a neural network called Word2Vec that really made Mikolov his career. He was, of course, immediately purchased by Google, and this is why Google does text prediction. If you type, it's exactly using this and now much more improved versions of this, like word glove and other kind of stuff. But essentially what it does is like, you can't just, if I give you a sentence, you don't look for just frequency analysis. That's already pretty good. But as you saw, the sections of archive, frequency analysis is certainly not good enough. What it does is it creates a window, and it slides these two windows, and it tries to minimize this partition function. So you can tell that Mikolov was clearly a physicist, or he had physics training. And if you try to minimize this, and it'll give you an optimal vector space in which to embed this. So basically what you do is you take the delta function representation of your word, you list all of the words that appear in a document in a delta function, what they call one hot, but just a delta function. So you just list them out. The first vector is 1, 0, 0, 0, and then 0, 1, 1, 1, 0. And you feed this list into this partition function over the window. So the window measures the distance between words within your document as well. So that gives context. So if you iterate this through the neural network, and it'll give you an optimal vector space in which these words are represented. The interesting thing is that in this vector space, you get very nice, because now every word which started off as a delta function, a vector, becomes some very funky vector, which are determined by how words are related to each other by their distance within a sentence, statistically. And so you get things like, let's take the vector of the word corresponding to man, plus the vector that corresponds to the word king, and then that's a new vector, there's a value. I subtract the word that corresponds to the vector, subtract by the vector that corresponds to the word woman, it's a new vector, and you look for what is the closest vector to that in cosine distance. Very quickly, Google finds that the closest word is queen. So that's actually quite nice. So if we did this just for the titles of archive, and you can find these wonderful things. So if you add the word bosonic plus string theory, and you ask what is the closest word that has the vector that's equal to the sum of these two words, and it's actually open string. It's wonderful. My favorite one, of course, is this. If you add the word string theory to Kabi-Yao and subtract M theory, and you ask what is the closest vector, just having, I want to emphasize, all we have seen is 1.5 million titles. We haven't even done abstracts. We haven't even done abstracts because I don't know how to strip LaTeX from, it's just too much. Dave Berman says it's not worth it, but maybe it's not. But you just need large parallel clusters of graduate students for this. But then you ask what is the word that corresponds to the vector that's closest to this difference, and it just returns G2. That's wonderful. But of course, you also, this is a highly biased sample because there are trillions of these, and I've given you my favorite ones. It also gives them lots of nonsense. But maybe they're not nonsense. Maybe that's the next direction you should pursue. Because, if I wonder if, so here's something I should do, which is to compute this to all papers prior, with abstract, in fact. Compute just the abstract and titles of all papers prior to 1998, right? And do this thing, and I'm going to do ADS plus dbrain is equal to what? Could I have predicted that the word is holography? I don't know, probably not, because we don't have enough sample for that. We're certainly after Madesena's paper, it would definitely give that because of all of the contextual information that we have statistically from this. But a challenge to you is there a way to have predicted that in some sense, and how do you measure such a possibility? Don't know. But this is fun. This is just so much fun doing. And it just let me to finish up. I can give you an example of something that is truly fun, which is, this vector space. You can start to say where there are similarities between the vector spaces across the sections, right? And even with the title, you can very quickly get to like a fairly diagonal matrix. So this is just a similarity score. So HepTH is like HepTH titles. HepTH is not like HepPH titles and so on. That's just you can do some cosine distance to assign a score. So it's more or less diagonal. Of course, if you included the abstracts, this is going to even get more and more diagonal, in the sense that the linguistic nature of HepTH is very different from a very close related field of HepPH, even though the words that appear in them frequency-wise are the same. Model, quantum gravity, blah, blah, blah. And yet, even just the titles show that this is pretty much diagonal. So that's good. And now here's a very interesting bit. If you try this with Vixra, in this crowd, I can say that, this. So what we wanted to test is that, is there a difference between science, non-science, and crackpot? Right, Vixra are completely crackpots. So those crackpots do not even have a self-consistent language for their own titles. They cannot distinguish what they call HEP or GR string theory. Even though they use the same words, they don't know how to string them together to make meaningful syntax. Even their titles, you can tell from this level, which is great. I mean, it shows that at least whatever the hell we're doing, even though some titles, you read our titles, they seem pretty random. But if they are not random, they're consistently science. And if you check that with something non-science, it's sort of as a base test. So we chose the Times of India just because they're freely available. This is sort of our baseline test, the null hypothesis. The least consistent one is Vixra, because they're just completely random strings of words, which is very good to know that whatever the hell we're doing is still science. I think this is pretty much it.